Thanks for tuning into this Revision Zone maths video. In this video, we'll be calculating the derivative of the sine and the cosine function. So the first result we're going to work towards is actually calculating the derivative of the sine function. We're going to do it two ways. We're going to do it graphically, and then we're going to do it formally using the limit definition of a derivative. So let's think about doing this graphically. So you can see on the right-hand side of the screen, we have a sine graph, and then just below it, we have a cosine graph. And if you take a look at the result we're trying to prove, we're trying to prove that, or show rather, that the derivative of the sine function is actually the cosine function. So let's start to think about this. So we know that derivatives are basically gradients. So our approach is going to would be to go to the sine graph and sort of by eye estimate what the gradient's going to look like, right? And then we'll be able to argue that actually the gradient, if we were to plot the values of the gradient on another graph, we will get the cosine graph. So let's do this. So first of all, if I come to this point here at the origin, I know that really at that point the tangent is going to be sort of pointing upwards in the positive quadrant. So the gradient at that point is actually going to be positive. I'm going to say it's going to be reasonably positive. Then if I come to this point sort of in the middle of the first part of the peak of the curve, then again, if I do a tangent there, the tangent's not going to be as steep as it was for the first point, but it's still going to be a positive gradient. The tangent's going to have a positive gradient. When we get to the top, now, because it's a stationary point, we know that quite well from the definition of a stationary point. We know that the tangent's going to be horizontal, and therefore the gradient is 0. And if I carry on, now the gradients are going to go from being positive to being negative because the tangents are going to be sloping downwards. So here we're going to have a negative gradient. And then if I come further down where the graph y equals sine x intersects the x-axis, actually the gradient's going to be even more steep, negative. So I'm going to just say it's negative, negative. And then finally, from this point onwards, we come here and the gradient starts to become slightly less negative. So I'm just going to say it's negative. And at the bottom, we get to another stationary point. So the gradient there is going to be 0 by definition of a stationary point. And now it starts to turn around. So now the gradient goes from being 0 to being sort of positive, of course, right? And finally, as it starts to come up, it gets even more positive. So we've now got an idea of what's happening with the gradient of our red curve. Now let's think about how that translates to the blue curve just below it. So I'm going to do that in a slightly different color. So let me pick green, for example. So for the first point here, you see, the y value of that is actually quite high. The y value is positive, right? And then as we carry on, the y value gets less positive, right? And then the y value gets 0. And the point we're trying to make is as follows. Let me write that down, right? So the gradient of the curve, of the red curve, let me say that, which we know is y equals sine x, right? Let me put that in big brackets. Can be plotted on a new coordinate system, and the blue curve, which is obviously y equals cos x, right, is such that the y values of the curve at a point, say, x, y, what I mean is, in other words, at the x coordinate x. So the blue curve is such that the y values of the curve at the point xy, in other words, at the x coordinate x, are in fact the values of dy by dx, right? Perhaps I should say that in brackets, are the values of the gradient of the red curve, right? So we can see that here, which is, let me get that. So here, the gradient is going to be positive, and it's going to be actually reasonably positive, so we get a very high value for y here. Then the gradient here is going to be still positive but less positive, so we still get a positive value for y here, but we actually get a y value which is smaller than the one we had here, right? And then finally the gradient there is 0, so the y value here better be 0, right? So if we carry this on and then see, well, okay, so let's think about this point here. Now the gradient is negative, so the y value better be negative on our next curve. So I come here to the, and then the y value is of course negative. And then we continue this on, and here, you know, the the gradient is very, very negative, so the y value has to be very, very negative here, which of course is going to correspond to about here, right? And so we mark that, so the y value is very, very negative. And we basically keep this up, and we see that so here now the y value is still negative, sorry, the gradient is still negative, but it's not as negative as it was there. So the y value for this x value here is actually going to be negative, but it's not going to be as negative as for this x value there, which was the y value was there, right? So if I mark that again, so we're going to get uh, negative negative y value, and then finally for the gradient being 0 there, the y value is going to be 0 there. So if I mark that too, and likewise if I just jump to the end, so here the gradient is now positive, it's very, very positive, right? So the y value correspondingly is going to be very, very positive. So I'm just going to mark the end value there. And in fact, from what I've done, it should be visible that if I was to draw these vertical lines, then what's happening is the gradient is corresponding to the y value at these points, right? So just doing this sort of graphically, we can start to get a sense of how the gradient's behaving on that red curve. And obviously, this is not a proof. This is just sort of an intuitive description of what's really happening. And we can see intuitively that actually it shouldn't come as a surprise that the gradient or the derivative of the sine curve is actually going to be the cosine curve. The only thing I really need to add is all this. So the graphs have been drawn in radians, right? So these graphs have been drawn in radians. So in other words, the x-axis is using radians and not degrees. Let's now see the exact same result we got a feeling for earlier. Now let's see an actual proof for it. So an actual argument, a formal argument showing why it's true. So because we want to differentiate sine x, let's define sine x to be our function f of x. Then we know that we want a derivative. Well, a derivative by definition is going to be f of x plus h take away f of x, and the thing is that I've got to be divided by h, and then we take a limit. That's what a derivative formally is. So we need to then write down this in terms of sine x. So sine x at x plus h is sine of x plus h, and then we take away sine x, and then we divide everything by h, and of course the limit is still the limit is still there. Now, to be able to make progress here, we're going to need to find a way of expanding this sine x plus h. But luckily, on the A-level syllabus, we actually have an identity. So we have an identity which says if I have the sine of a plus b, that can be expanded out to give me the sine of a, the cos of b, plus the sine of b times by the cos of a, right? So let's use that statement to be able to expand out the first term in our numerator. So I write that down. That's going to come along to the right. So the expansion is going to give me sine x cos h plus sine h cos x, right? So we've now done the expansion. That thing there is equivalently that thing there. But what we need to do now is write down the other term that's part of the numerator and just copy down whatever's in the denominator because that doesn't really change. So we've got that. Now at this stage, things need to be tidied up here. This is a bit too involved. The good news is I've got a sine here and I've got a sine here. So let's combine them. So what I'm going to do is the limit's obviously going to come along for the ride for now, and I'm going to combine the signs. So sine x cos h minus sine x. So I've moved that sine x from the far right to sort of closer to my first term. And then I've got the other term in the numerator, which is sine h cos x. Okay, and I still have the h as a denominator. Now at this stage, I actually want to factorize things to even tidy them up further. So I'm going to factorize a sine x from here and from here. Okay, so I get sine x and then brackets, here comes the factorization, it's going to be cos h minus 1. Okay, and then the other term, which was obviously this thing here, is still going to be there, but I'm going to write it so that the x is first and the h is afterwards. So cos x and then sine h. Now, the good news here is I actually, if you take a look, I have an x term here, and then I have an x term here at the front, then I have a h term at the sort of second, and then I have a h term second. So I've organized it in a reasonably systematic way, and of course I shouldn't forget my h in the denominator. Now at this stage, we're going to use some rudimentary algebra. We know that if we have a term like a plus b over c, that can be split up into a over c plus b over c. So using that, I can go back to my limit expression. Let me just draw a little line to say this is just a side comment. It's not really part of the main calculation. It's just being used. It's just being used as an aside. So I'm going to split things up, and when I split things up, I'm going to get sine of x and then cos of h minus 1, and this is going to be over h. So this is like my a over c, right? A over c here. And then I have plus the cos of x multiplied by the sine of h, and obviously that's going to be over h. And now this is like my b over c. So here. So I've managed to go from something that looks like that, which is here, to something that looks like that, which is here. So now we have this, I actually do need to say something else. Say if we've got something of the form alpha beta over gamma, then algebra tells us we can actually rearrange that to say alpha times by beta over gamma, right? So we're going to now use that idea and basically rewrite this as the limit h tends to 0. I can write the sine x by itself times by the cos of h minus 1 over h and put some brackets around here maybe. Okay, and then the same thing here, the cos x by itself, and then times by, put some brackets around sine of h over h, put some brackets around. And then of course there are these big brackets on the entire term because obviously I've not really done anything as far as algebra is concerned. This thing here is exactly the same as that thing there. But the good news is we have actually made progress, even though it might look like we're just moving stuff around and not really getting anywhere, right? At this stage, what we need to do is because we know the limit applies to everything in the bracket, we've got to expand the limit to go inside the bracket. But as we do that, we can save ourselves a bit of work because the limit is not going to impact anything purely in x. So these things at the front are purely in x, and these things actually in the big brackets here and here are purely in terms of h. So the limit is actually really only going to apply to them. So let's rewrite this. I can write it here to make a bit of room. So I can say sine x, because the limit, as I say, does not apply here on the x. And then the limit does apply to cos h minus 1 over h. And then the limit's going to apply to the second term, but it doesn't apply to the first part of it because that's only in terms of x. So it's going to be the limit as h tends to 0 of sine h over h. At this stage, we need to go back to the result we worked out in the previous video of this series, which is we precisely sort of figured out what this limit was and what this limit was. If I'm not misremembering, this limit was actually, I think, statement 3 or yeah, statement 3 that we actually worked out, result 3 in that video, and this was result 2 that we worked out in that video. We know what these limits are going to evaluate to give us. This limit is going to evaluate to give us effectively 0, and this limit is going to evaluate to give us 1, right? Since we know that, then the first term here, which is sine x times by the limit, is just going to be sine x times by 0. So that term is basically going to die, right? And then this term here is going to be cos x times by 1, and that term is going to give us cos x. So we've actually managed to work out formally the derivative of sine x, and we've been able to show that it's actually cos x. So result 2 tells us that the derivative of the cosine function is actually the negative sine function, not quite the sine function. We can run through this at a slightly quicker pace. So we've got graphs of the cosine function here, well, graph of the cosine function, and then the other graph we have is of the negative sine function. And immediately we can actually see for x going from 0 to about pi, we can see that the curve is pointing downwards, which means the gradients are negative. And because the gradient for this entire section of the curve is negative, we see that the y values for x being between 0 and pi for this green graph, all the y values are actually negative for the exact same region. The other positive thing is if you see the gradient is 0 at x equals 0 and the y value here is 0 at x equals 0. And again, the gradient is 0 at pi, and the y value here is 0 at pi. And then for the other half of the curve, we actually have the gradient is positive because the curve is sort of facing upwards, it's increasing. And then we see for the exact same part of the curve from x equals pi to x equals 2 pi, the y values of this curve are entirely positive. I should have said this in the last example, actually. We need not consider the x values going from negative infinity to positive infinity in this case. And the same would apply to what we did in result 1. And the reason for that is these curves are periodic. So they're going to repeat themselves again and again and again and again. So the minute we know what the gradient is or what the derivative is just between x equals 0 and the first time the curve starts to repeat itself, that's basically sufficient for us to be able to say that's what the derivative is going to be for this curve everywhere. So let's write this down. What I mean is the gradient of the blue curve, which of course is y equals cos x, okay, can be plotted on a new coordinate system. Can be plotted on a new coordinate system. Okay, so the green curve, which of course is y equals minus sine x, is such that the y values of the curve at the point xy, so in other words, what I mean by that is i.e. At the x coordinate x, are in fact the same as the values of dy by dx. In other words, the values of the gradient of the blue curve. So this at least goes to show visually that the derivative of the cosine function is actually the negative sine function. And as before, the only point I actually need to mention is the fact that all this is done in radians. So radians are used on the x-axis. And of course, the reason why we use radians is because we saw in the last video that it's in radians that limits of sines and cosines sort of give out much more sensible things and they actually exist. Whereas if you do them in degrees, then they don't always exist. So let's work out this result more formally. So it's a proof. The function, obviously, because we want to differentiate the cos function, let's define f of x to be cos x, which tells us that the derivative, obviously, using the definition of a derivative, we can just write the standard thing down. We've seen this lots and lots of times now. Since our function is cos x, then the definition gives us cos of x plus h, take away cos x, and the whole thing is over h, and of course the limit is still there. Right, so now at this stage we need to use an identity from the A-level syllabus. This is very much like what we did for the time when we differentiated the sine function. The identity in this case is going to be different. It's going to be the corresponding cosine identity. So cos A plus B is identical to cos A cos B minus, this time, sine A sine B. So let us take A to be x and B to be h and apply it to this term there. So we end up with, oops, I should write this in black perhaps. So let's change. So we have cos of x cos of h minus sine of x sine of h, and of course everything else, which is this the term in the numerator and then the denominator, comes along for the ride for now. So we just have cos x and the whole thing is over h, of course, and it's being taken the limit of. So now it's about tidying this up so that we can actually evaluate these limits. So let me rewrite this. Let me rewrite this in a way where I combine that term with that term and actually factorize the cosine out. So I can just take the cosine out, and then inside the brackets I'll have cos of h take away 1. And of course you can check that when I expand this, I'm going to get this term cos x cos h, and then cos times by minus 1 is going to give me the minus cos term. So I've taken care of this term, and I've also taken care of that term. So the term that remains in the numerator is just this sine x sine h term, which I'm going to write down now. So minus sine x sine h, and of course the denominator remains to be purely in terms of h. Now, at this stage, we need to really split up our fraction. Perhaps a set of brackets would help here because, as I mentioned when we did this for the sine, we've now got something algebraically of the form a plus b over c, right? So we can now split this up to say a over c plus b over c. So doing that in this case will give me the limit as h tends to 0, h, is cos of x, and then it's going to be cos of h minus 1 over h, and minus sine of x multiplied by sine of h, and this is over h. So perhaps to be a bit more accurate, what I should have said is not plus in this case, we actually have a minus, right? So the numerator had a minus b, and we can split that up into the sort of thing we've got on the right. So perhaps I'll just draw something here to say an aside, right? Uh, like in the case we did for the sine function, we still have to tidy this up further. And what we're going to use is, if we've got something of the form alpha beta over gamma, then we can keep the alpha out and we can just say it's the same as beta over gamma times by alpha. So this is just all aside. So let me write that down. So what we're actually going to have is we're going to have the limit as h tends to 0 of cos x times by cos h minus 1 over h, and then minus sine x times by sine h over h, and of course the brackets are still there. So now this is looking a lot more promising. We see that we have a function just in terms of x and a function just in terms of h, and again we have a function just in terms of x and a function just in terms of h. Since the limit is going to apply to everything inside the bracket, to the entire thing, it's going to be distributed across the bracket. But obviously the limit is with respect to h, so it's not going to impact anything purely in terms of x. Okay, so what I can write down is actually what I'm going to have is the cos x is just going to be there. So as the limit expands in, the limit is just going to apply actually to this thing here, the cos of h minus 1 over h. And then the sine x is going to be left alone because it's purely in terms of x. And the limit is going to apply to the sine x, or sine h, sorry, over h. And now these are standard limits because we showed this in part in the previous video in this series, that the limit for cos h minus 1 over h as h tends to 0 is actually 0, and the limit for sine h over h as h tends to 0 is actually 1, which then means that the first term here actually gives us 0 because cos x times by 0 is just going to give me 0, and the second term gives me minus sine x times by 1, which actually gives me minus sine x. So we've been able to formally work out the derivative of the cosine function, and we've shown that it's the negative sine function. We hope you liked this video and want to see more. Please do let us know in the comment section what you would like to see more videos on. And as always, please hit the like and subscribe buttons if you found this video useful. Thank you for watching, and we will see you in the next video.